Hello, welcome to Stat 7 479, Lecture 17. Right now we're kind of in the middle of our fourth and final key module, which is graphical models. And in particular, we're still in the process of defining the notion of graphical models. This is a relatively new concept, and it's a way to define multivariate distributions over p random variables. So when you have multiple variables. So in particular, we're finishing off today this section on directed acyclic graphical models, which relates to, and in particular, we're focusing on one particular parametric approach, structural equation model. So we're going to finish off that discussion. And then at some point today, we're going to switch over to the other class of graphical models which come up, which are undirected graphical models. Okay, so structural equation models, they're defined by conditional PDFs or structural equations. So in particular, we're focusing on the scenario where this is the linear. These are the linear models. So here, the linear Gaussian models involve xj being equal to the mean plus this quantity that depends on a, and these parameters a. And then we add some standard normal noise, and this is independent noise across the j. So you can think of this as like j linear models that are put together, but they interact with each other because they obviously depend on the parent. So the graph structure enters there through the parents of xj. And you can also think about it, as I mentioned, through conditional distribution. So xj given x parents of xj, so we're defining in some sense the conditional distribution of each xj given its parents, which is another way to define directed acyclic graphs, as we saw, because it's the product of those different conditionals. Then we have that this is going to be normal with the mean of mu j, and then plus the terms due to the parents. So this is akj plus akj, so this should be xk. And then with variance of sigma j squared, j equals 1 to p. So just to take a concrete example, or we'll just see this with two concrete examples that we've seen before. For that confounding scenario where, I guess this is not the confounding scenario, but the scenario where we have x1 is independent of x2, but x1 is actually conditionally dependent on x2 given x3, which is the scenario that we saw earlier. The only there's no parents of x1 and there's no parents of x2. So from a structural equations point of view, you can think of it as x1's just a standard normal, or just a normal random variable with mean mu1 and variance sigma 1 squared. X2 is a normal random variable with mean mu2 and variance sigma 2 squared. And x3, because it has the two parents x1, x2, in the mean, the conditional distribution is given by mu3 plus, and then we have the influences of x1 and x2. And so there's this very nice relationship between the parameters or the quantities of A and the graph structure, because if AJK is equal to zero, this means that there's no edge between xj and xk in the DAG. And the other thing that we learned in the previous lecture was this means that xj is conditionally independent of xk given the parents of xj union xk, and then if we exclude the variables xj and xk. Okay, and the other thing that we learned in the previous lecture was the matrix vector form. So the matrix vector form, which we wrote it out as okay, so here mu is equal to this mu1, mu2 up to mu p. So this is in r to the p. Obviously x is in r to the p, that's the random variable that we have. So I'll just write this out fully. Okay, and then we have A, which kind of encodes the graph structure. That's in r to the p by p, where A kj just equals to A kj. And note that here, so obviously AKJ equals 0 if and only if no edge between xj and xk in the graph. And then we have that that's epsilon 1. This is the kind of independent noise, and this is multivariate normal with a mean 0 and covariance of D, where D is this diagonal matrix. I'm going to use the notation diag for a diagonal matrix, sigma 1 squared, sigma 2 squared up to sigma p squared, and this is in R to the p by p, obviously, for the diagonal matrix. Okay, and so the other thing that you can do is you can rearrange things as we saw in the previous lecture. So you have I minus a times x equals mu plus epsilon, and so x equals, you can, because the graph is an acyclic graph, you can always invert this. I haven't shown why that's true, but it's to do with the fact that if it's acyclic, you can kind of rewrite it as you can permute the rows and columns to be a lower triangular matrix, which makes this invertible. And so therefore we have that x is multivariate normal with the mean I minus a inverse mu, and then the overall variance is, if we use the standard formula that we've seen for variance or covariance, it's I minus a inverse transpose. So this is like your sigma, and so this encodes the information about the graph structure. And so now we're going to look at the factorization perspective for DAGs. So, we know that from a factorization point of view. So what I'm actually going to do here is arrive at essentially the same conclusion that we have here. So we have that this is the multivariate normal distribution, where the matrix A encodes the parameters of the graph. And so we're going to arrive at essentially the same conclusion, but coming at it from the perspective of the factorization, which is another way to characterize the DAG. So we know that for a DAG, we can write the factorization kind of in this form, and then we also, as we saw earlier, the way that structural equation models are actually defined actually naturally lend themselves to DAGs, because they're defined in terms of their conditional PDFs where you condition on the parents, and so we know that so this is the form that we saw, and so clearly we have that fj of xj that's equal to okay, so this is the distribution, because it's this going from here to here. We're just using the formulas for the conditional PDF of a normal. Okay, and so if we look at if we now use this factorization formula, okay, then we can rewrite this as Okay, and so I'm just rearranging here. Once again, we can take the product of the exponentials into the exponential of the sums. Okay, and one thing to also note here is this is because D is a diagonal matrix, and we're taking the product of these diagonal elements of it. This is exactly just the determinant. So this is determinant of D. So this is the notation I'm using here. Okay, now to kind of go back to the form that we had earlier, I'm going to now convert to matrix vector form. So you can actually rewrite this as x minus mu and then D inverse okay, so this is just putting it back into putting it back into matrix vector form. So if you want to convince your, let me just so this is now. So here I'm going to use this notation. X tilde equals our x subscript x1, x2 up to xp. So this is a vector. And okay, so I'm just doing some rearranging here, and what we'll hopefully get is what we got from the earlier equation. So we're kind of just proving things a different way just to get a better understanding of what's going on. So what I'm next going to do is just take out the just going to take out this and invert this expression. So I'm going to have to go over 2 lines here. So I'm kind of just taking out this. So this is like our and then I'll just go over to the next line here. So this is okay. And so here, one thing to kind of note here is that the determinant of sigma actually equals to the determinant of D. And the reason, so this is not something that's actually obvious to you necessarily, but the reason is since A corresponds to a DAG, you can express you can express so sigma inverse equals I minus A. So let's take a step back here. So you can kind of rewrite this as so let's write this. Let's take a step back. And we have that okay. So this looks exactly like the form of the multivariate normal now. So we have here that sigma inverse here equals I minus A transpose D inverse I minus A. And so if you actually invert this, equals so I'm using properties of inverses of matrices here that you can potentially use here, and that just is equivalent to I minus A inverse D I minus A transpose inverse. And so that's exactly what we get up here. And so note that the mean is I minus A inverse mu tilde, which is exactly what we saw earlier. And the other thing to note is that the determinant of D is actually just equal to the determinant of sigma because I minus A is a lower triangular matrix with ones on the diagonal. Okay, and this, again, if you don't understand this statement, that's perfectly reasonable. I'm kind of skimming over it here. And that's since A is a DAG. I can certainly give you a more in-depth explanation if you'd like for that. It's a little bit involved, but so I'm not going to kind of talk about it here. But if you want a more in-depth explanation, you can kind of come to my office hours, or I can or send me an email. But that's why this is the same. So we can express this as this whole f of x1, x2 up to xp is just 1 over 2 pi to the p over 2. And then we have split of negative a half x minus I'm going to use this notation x minus m. Okay, and so here we have that sigma equals I minus A inverse D I minus A transpose inverse, and then we have m equals I minus A inverse mu tilde. And so therefore we have that x is multivariate normal with a mean of I minus A inverse mu, and then a variance of I minus A inverse D, or a covariance of I minus A inverse, and then this is transpose. And that's like, again, using properties of matrices and inverses, the transpose of the inverse is the same as the inverse of the transpose. So note that this equation here corresponds exactly to this equation here. And so we get, like, essentially, I just wanted to come at it from two different perspectives and see that we get exactly the same answer. So we have we have the structural equations model perspective, where you just sort of see it as the structural equations, and then we have the factorization perspective, where we use the conditional distribution. So just to summarize a little bit, so SEM's natural parametric models for DAGs. And graph structure encoded in the parameters AKJ. So clearly, if AKJ is 0, that means there's no edge, and so on. And the other thing I'd like to say is that another way to think about it is that it's they correspond to P models, like P, I'd say conditional models. P conditional models, and this could be like linear. I've shown them so far with linear models, but I'll show you shortly that they extend to GLMs as well. P linear models, where xj is response and x of the parents of xj are the covariates or features. So this is an interesting kind of connection between what we see, like DAGs are actually an unsupervised model. You have x1 through to xp, but you can actually, there's actually this very nice connection to what we've already learned with supervised learning with linear models, GLMs, and so on, is that you can kind of see these structural equation models as just, they correspond to P conditional models, which you can think of them as linear for now, where xj is a response and x parents of xj are the covariates. So it's actually, so this has a natural connection to regression or supervised models. So a lot of what we learned in the first 3 modules is actually very relevant here. So in particular, and then to further that point, there's natural extensions to GLMs. Where you can say that xj given x parents of xj, that has a, I'll just use this notation, GLM. So I'll spell this out a little bit more. xj given x parents of xj is defined by the GLM, and remember that the GLM is just an exponential family with the log partition function. I'll use the notation a, and then the base measure h, and then like the sufficient statistic, we'll just say t of x is equal to the identity. So that is just you can rewrite that as in other words, fj of xj given x parents of xj is equal to it's going to be hj of xj and then x of some of summation, like the k is in the parents of xj, and then akj xk. So this is like your theta basically, just like we saw with the GLMs, and then times xj, and then minus, and then a of summation k in parents of xj, akj, xk. So this is again like your theta. So this is like your this is your base measure. Okay, so this is another. So this naturally extends to GLMs as well, because it naturally defines the conditional PDF. So this is kind of an important connection to kind of understand about GLMs and sort of or this connection between structural equation models and P sort of respect like P individual models, where you can imagine that the xj is the response and then all of its parents are like covariates. And essentially we just put all those together through, and then we put all conditionals together through this factorization. And that always defines a valid distribution for a DAG. So that's pretty cool that you can you only need to define the conditionals, and each conditional is just like a separate linear model or GLM. And you only need to, and then once you have those conditionals, that completely tells you the whole joint distribution. So from these conditionals, we can calculate joint PDF. Okay, so this is kind of a pretty nice sort of result and a nice way to interpret these DAG models. And this gives you a natural parametric way to define DAG models. So just to give a quick summary of DAG models. So just returning again, we have this so it's defined by a directed acyclic graph. And I'll use this notation G equals VE, where V is equal to the set of nodes x1, x2 up to xp. E is equal to this set of edges xj, xk, where xj is parent of xk. And then the connection to the distribution is through, there's one which is through factorization, which is that the joint is just given by these conditionals. So once you know all the conditionals, you know the joint. And then it's also this important connection through conditional independence, which is that xj is independent of xk given the parents of xj union parents of xk, but not including the points xj and xk. So this is true, and if and only if no edge between xj and xk in your graph. So this again shows this kind of shows the connection between the graphs and the conditional dependence statements, which is related to the probability. And so these are kind of the two ways to show the connections. And then the final thing is that structural equation models provide natural way to encode information about to encode or to provide a natural way to sorry, I'll get this right, to give a parametric model for DAG models. Okay, so yeah, this is a relatively potentially new concept to some of you. So just go through the notes carefully and let me know if there's any particular questions that you have on this. Okay, so that's kind of wrapping everything up that we've covered for DAGs, and now we're going to move on to undirected graphical models. So undirected graphical models, so they're defined by an undirected graph. So I'm going to use the notation UG here. So G here is equal to VE. So once again, V is equal to X1, X2, up to XP. And then E is equal to, again, we have pairs of nodes. But order xj, xk does not matter. So the edge xj, xk, and xk, xj are the same edge. Okay, so let's just to be concrete. So we could have x1, and note that there's no arrows here because this is undirected. So this is the edge set here is just clearly x1, x3, x2, x3. To take another example with 4 nodes here. And the edge set here is this 4 edges, x1, x2, x1, x4, x2, x3, and x3, x4. Okay, so this is the an undirected graph. So it's like a directed graph, but there are no directions here. And then the question is like, how does this connect to multivariate distributions? Multivariate distribution, which is clearly f of x1, x2 up to xp. And in particular, there's, so there's two, like a lot of the ideas that we use from DAGs are going to be used here for undirected graphs, but we'll see that, the conclusions are a little bit different. So 2 connections. So one is obviously through factorization of undirected graphical model, like undirected graphical model. And then the other one is through conditional independences. Okay, so let's first talk about factorization. So the factorization in the case of the undirected graph is actually a little bit more complicated. So it's not easy to express in terms of conditional PDFs, since there are no directions, and in particular what that means is no directions or no ordering of the variables. Okay, and so instead we express in terms of potential functions. And I mean, this is a pretty new concept potentially for a lot of you. So we're gonna kind of go through it slowly and give an example. So potential functions. So what that means is that so the factorization is f of x1, x2 up to xp is equal to 1 over z. I'll explain what these mean. So then we have the product, and this is where the graph structure enters. Like if we have an edge between xj and xk in E, then there's a potential function xj, xk. Okay, so what do all these things mean? So z here is like a normalization. This ensures that PDF integrates to 1. So remember that all PDFs have to integrate to 1. So psi jk of xj, xk is actually, so this is a potential function. It's not a PDF, but it does have the property that phi jk of xj, xk has to be bigger than or equal to 0. Okay, and so this is potentially a very weird and maybe a little bit obscure definition. So I'm just going to give you a concrete example to begin with. So we're going to go back to a very nice example that we've seen before, which is just that x1, x2 up to xp is multivariate normal with mean mu and covariance sigma. Okay, and so, factorize this in terms of a graph, of an undirected graph, G equals VE. So it turns out that we can, and so let's see how we do that. So we know that f of x1, x2 up to xp is and then okay, so this is just the general form of this. And so it's not necessarily obvious how this converts to the potential function, but let me kind of do something. Let's use it. Let omega equal to sigma inverse. So this is like the inverse covariance. Okay. So then you can kind of rewrite this as so we're going to just change the parameterization now to the inverse covariance, which means that f of x1, x2 up to xp is equal to the inverse covariance, because if you take the inverse, the determinant also just gets inverted. So the it just becomes the numerator rather than the denominator. And then we can re-express this as x minus mu transpose. And then omega x minus mu. So how is this useful? What that kind of means then is if we re-expand out the re-expand this out, this is equivalent to x of we're going to say summation j equals 1 to p, summation k equals 1 to p, and then it's going to be negative a half of xj minus mu j omega jk, and then xk minus mu k. Okay, and so why this is going to be useful is now that we have, you can write this out as the product of j equals 1 to p xk minus mu k. And now let's split it up into the diagonal and off-diagonal terms. You can write this as the and then product of j not equal to k Okay, and so note that let's say omega jk equals 0 implies no edge in graph, g equals ve, and then omega jk not in, I'm just rewriting the same statement, implies that there is an edge in the graph. Okay, and so what that means is that this whole factorization you can write this out as okay, and then can always multiply this by and you'd need to divide this just to take this all to the power of 1 over, and I'll define this again shortly, the number of neighbors of xj. I'll say what that actually is. The reason you need to do that is to make sure that you don't kind of multiply things through too many times. It's 1 over, it's going to be 2 over the number of neighbors because there's double counting. So what is the number of neighbors? So the neighbors, this is like the parents. And so this is equals xk such that xj, xk is in E. So you can think of it as like, it's like, so this is like parents, but with no direction. And again, the reason why we're doing this is to make sure that we don't double count edges too many times. So in particular, just to wrap all that up, so this is like your 1 over z, and then you have and I'm just writing this over 2 lines, but okay. And so this whole thing is just your psi jk of, this is your potential functions, okay? So the important thing to note here is that, well, there's 2 takeaways. We have a form for the potential functions. So recall that the factorization is okay. And the other thing that we note here is that for the multivariate normals, we have psi jk of xj, xk. So that this normalization here just is something that doesn't have an x in it, and it makes sure that the whole integral is just 1. And if you look at these cxjk's, they're equal to exp of okay, and so note that the other thing to note is that if you look at the inverse of this covariance matrix, that this is what encodes the graph structure. So omega jk is equal to 0 if and only if no edge between xj and xk. Okay, and so let's just do a couple of examples. So we can clearly see here that if you write out the inverse covariance matrix, so this is equal to, so sigma inverse should be omega, all the diagonals are going to be positive. And then we have an edge here, but we don't have an edge from we don't have an edge from 1 to 2, so those are zeros. Okay, and so, yeah, the other thing I kind of haven't mentioned, but is going to be true based on properties of matrices. So since sigma is going to be positive definite, and positive definite and symmetric, the inverse is also positive definite. And symmetric. Okay, and then just to give one more example, so if we look at x1 through to x4, then we have an edge from x1 to x2, so these are non-zero. There's no edge from x1 to x3, so that's 0, and then we have an edge from x1 to x4. And then because of the symmetry, we're going to have no edge here, and is that correct? Maybe not. Let me just. So, in fact, there's going to be a 0 here. Okay, so this is what how the inverse covariance matrix encodes the graph structure. So this also provides a way to parameterize the distribution, but through the inverse covariance matrix. And this is for an undirected graph as opposed to what we saw earlier with the directed acyclic graph. And again, this is potentially quite a new concept and a bit maybe difficult to get your head around at the moment. You'll hopefully just become more as we go through it more, it'll hopefully become a little bit clearer. And we're actually going to talk about ways to do parameter estimation and things in these graphical models shortly. Not probably this lecture or next lecture, but in lectures 19 and 20 probably. Okay, so now so that was factorization, and then the other question is conditional. This is the other way to relate graph structure to the concept of probability of conditional dependence. So recall that the general idea of graphical models is that edges are non-edges. They encode information. They encode conditional dependence or independence in information. Okay, so I just wanted to remind you of what happens for DAGs. This is done through xj is independent of xk given its parents. And that's going to be true if and only if no edge between xj and xk or say no edge between xj and xk in G. So for undirected graphs, no concept of parents because the edges are undirected. But what's an analogous concept? But an analogous, it's not exactly the same, but an analogous concept is neighbors. So neighbors, we use the term because they're kind of equal. So if xj is a neighbor of xk, then xk is also a neighbor of xj. So we're going to say the neighborhood set of xj is equal to xk such that xk is in E. And then this relationship is reciprocal. Okay, and so just to give you some examples, x1, x2, and x3. So the neighborhood set of x1 is just x3. The neighborhood set of x2 is equal to x3. The neighborhood set of x3 is equal to x1 and x2. Similarly, for this graph, the neighborhood set of x1 is x2 and x4. The neighborhood set of x2 is x1, x3. The neighborhood set of x3 is x2 and x4. And the neighborhood set of x4 is equal to x1 and x3. And so you kind of clearly see the symmetry in the relationships here, which you don't have for the DAG, that if xj is a neighbor of xk, then xk is a neighbor of xj. And so because these relationships are undirectional, that's why. But when the relationship's directional, they're not going to be reciprocal necessarily. So the child of a parent is obviously not going to be the parent, not necessarily going to be the parent of a child. And in fact, for DAGs, it's impossible for the child of a parent to be the parent of a child. Okay, and so so then how does this connect to conditional independence? So we have conditional independence. So what we say here is, so recall what we saw for DAGs and parents. We're going to get essentially the same thing where we replace parents with neighbors. So xj is independent of xk given the neighbors of xj union with the neighbors of xk, excepting but not including xj, xk. And that's going to be if and only if no edge between xj and xk in the graph. This is now an undirected graph. Okay, so now let's, to finish this this lecture, we're going to go through these two examples and see what they mean. So for example 1, we have x1, x2, x3. So clearly what this means is that x1 is independent of x2 if you condition on its on all the neighbors, and so that's x3. And then you have that x1 is dependent on x3 if you condition on all its neighbors, which are x2. And then x2 is dependent on x3 if you condition on all its neighbors, which are x1, because x1 is a neighbor of x3. And then we're going to look at x1, x2, x3, x4 here that we did the second graph. So we clearly see that x1 is going to be dependent on x2 given the neighbors of both, which includes both x3 and x4 because they're neighbors of x1 and x2. We're going to have that x1 is actually independent of x3 given the two neighbors, x2 and x4. x1's dependent on x4 given the neighbors, which are the neighbors of x2 and x3 again, because x3 is a neighbor of x4 and x2 is a neighbor of x1. And then we have x2 is dependent on x3 given the neighbors, which are again going to be x1 and x4. and then x2 is independent now of x4 given the neighbors, which are again going to be both everything else, which is x1, x3, and then you're going to have that x3 is dependent on x4 given the neighbors, which are again going to be x1 and x2. Okay, so therefore we have two characterizations. Just like we do in DAGs, one is the factorization. Which is that so there was this kind of this sort of weird notion in terms of potential functions. So this is like the potential function. It's not as clean as the case of DAGs because you kind of can't just build them up through conditional independences. And then this is the normalization. Okay, and that that kind of tells you, like, that ensures that everything integrates to 1. And then we also have the conditional independence / dependence, which just asserts that xj is independent of xk given it's the parents of neighbors, sorry. Neighbors of xj and xk, but not including xj and xk. And this is going to be true if and only if no edge xj in G, which is VE. And then the last thing I just wanted to point out as the other third main takeaway today is that for the multivariate normal, graph structure is encoded in the parameter omega, which is sigma inverse, i.e. like omega jk is equal to 0 if and only if no edge xj xk in okay. So those are sort of the main takeaways from what we've learned about undirected models, graphical models so far. So there's a lot of new concepts and a lot to take in, but we'll go through some more examples and go into more depth on it in the upcoming lectures. Okay, thanks very much.